Hidden in the heart of a distant galaxy lies Phoenix A, a black hole so massive it could be the largest ever discovered. But how big can these cosmic giants truly get? Tonight, we'll explore the mystery of Phoenix A and what it means for our universe. If you enjoy the journey, please like, subscribe and share, and tell us in the comments, do you think we've already found the universe's biggest black hole, or is an even larger one still waiting to be discovered? Thank you for watching. Now let's begin. Across the largest scales of space, matter arranges into a web of filaments and knots that extend for hundreds of millions of light years, with vast empty regions lying between. In these dense knots, gravity binds together the most massive self-contained systems in the present universe, known as galaxy clusters. A cluster is not a casual gathering of separate galaxies, but a single gravitational structure that holds thousands of galaxies' immense stores of hot gas and a dominant halo of dark matter. The combined mass is so large that the space around the cluster is curved enough to bend the paths of light passing near or through it, an effect observed as the distorted appearance of more distant galaxies in the background. In this regime, the unit of structure is no longer a single galaxy, but a system of many galaxies sharing one gravitational well and one surrounding medium. Clusters grow over billions of years. Smaller groups fall along the filaments and merge, building larger units step by step. When these mergers occur, the galaxies largely pass through one another, but their diffuse gases collide and slow, creating shocks and long wakes that can be mapped. The outcome is an atmosphere of hot gas filling the space between the galaxies. This intracluster gas is very thin compared with air at Earth's surface, but stretches across millions of light years, and it is heated to tens of millions of degrees. At such temperatures, it shines in X-rays rather than visible light. So X-ray observatories reveal the shape and structure of the cluster atmosphere, while optical instruments trace the positions and motions of the galaxies themselves. The mass of a typical bright spiral galaxy spans about 100,000 light-years across. A large cluster can span 10 million light-years or more. Even though the galaxies in a cluster contain countless stars, most of the ordinary matter is not locked in those stars. It is in the intracluster gas. This fact is central to the physics of clusters. The gas cools as it radiates energy, and in the densest central regions the cooling time can be shorter than the age of the universe, which means that without some source of heat, the gas would be expected to flow inward and condense. Systems with dense, relatively undisturbed cores are often called cool core clusters. Others show clear signs of past or ongoing mergers, with asymmetric gas distributions, cold fronts, and shock edges at scales of hundreds of thousands of light years. These different appearances record the assembly histories of the clusters and the energy exchanged among their components. Dark matter dominates the total mass of a cluster. It does not emit or absorb light, but its gravity controls the motions of the galaxies and the profile of the intracluster gas. Astronomers infer the dark matter distribution by fitting the motions of member galaxies, by modeling the temperature and density of the hot gas, and by measuring how the cluster distorts the images of more distant galaxies behind it. All three methods point to a deep potential well that is smooth on large scales and steeper toward the center, shaping both the orbits of galaxies and the pressure of the hot gas. The intracluster medium is not static. Galaxies moving through it at several hundreds to over 1,000 kilometers per second experience a wind of hot particles. That wind can strip away the galaxy's own gas, leaving tails that shine in X-rays or an emission from warm gas. This stripping can reduce or halt star formation in affected galaxies. On yet larger scales, bulk motions and turbulence stirred by mergers redistribute heat and mix metals, the heavier elements produced by stars and supernovae that have been pushed out of galaxies into the surrounding medium. Seen across the spectrum, a cluster presents a composite picture. In visible light and near-infrared images, the densely packed galaxies crowd the central region with a brightest member often near the center. In radio maps, diffuse features appear where relativistic electrons spiral around magnetic fields, marking past shocks or activity from central engines. In X-ray images, the cluster's atmosphere dominates its brightness, tracing the depth of the gravitational well, and its temperature pattern revealing disturbances or smooth cooling. Together, these views show how stars' gas and gravity share energy and momentum across scales measured in millions of light-years. Among known clusters, a small number stand out for their extreme luminosity in X-rays, their great mass, or their unusually dense cores. The Phoenix cluster is one of these rare systems. It lies at a distance of about 5.5 billion light-years, a look back to a time when the universe was roughly 2/3 of its present age. It first drew attention in a survey sensitive to the subtle imprint of clusters on the cosmic microwave background, a uniform field of radiation left from the early universe. Follow-up observations in X-rays and in optical light established that Phoenix is extraordinarily bright in high-energy emission and hosts a very large reservoir of hot gas. The total mass of the system is several million billion times the mass of the Sun, placing it among the most massive known. Its central region contains very dense gas with short cooling times, which is uncommon because many clusters show signs that heating processes counteract such cooling. The presence of a rich galaxy population is expected in a cluster of this scale. The detailed distribution of those galaxies shows a concentration toward the center, as expected for a deep gravitational potential. The space between them is not empty, but filled by the hot atmosphere that carries most of the ordinary matter. Measurements of the gas temperature and density yield an estimate of the pressure profile, which in turn reflects the underlying mass that shapes the cluster. Observations at different wavelengths provide consistent evidence for a large centrally peaked system, in which the cluster atmosphere plays an active role. The physical conditions in Phoenix illustrate the general principles of cluster physics. Gravity gathers matter from large scales, builds a deep potential well, and compresses gas into an extended atmosphere. Radiative cooling in the dense core acts over cosmic time to lower the gas temperature. Motions induced by mergers and by the passage of galaxies stir the atmosphere and spread energy and metals. The ratio of gas mass to total mass, the temperature pattern, and the surface brightness profile together show that most of the cluster's ordinary matter resides outside the galaxies, and that the cluster as a whole is a long-lived gravitationally bound system rather than a temporary alignment along the line of sight. The study of clusters like Phoenix provides constraints on how structure grows in the universe. Their number as a function of mass and time serves as a test of cosmological models. Their internal makeup, including the balance among stars' hot gas and dark matter, reveals how different forms of matter behave in deep potentials. Their hot atmospheres carry imprints of past mergers and the motions of many galaxies sharing one medium. In this way, a cluster offers a clear view of gravity at work on the largest scales accessible to direct observation. In the Phoenix cluster, the combination of total mass bright high-energy emission and central gas density makes the system a clear example of a massive mature node in the cosmic web, extending across many millions of light-years, and shaped by the steady action of gravity over billions of years. The Phoenix cluster lies at a distance of about 5.5 billion light-years, making it both remote in space and ancient in time. Light that now reaches Earth left the cluster when the universe was only about 2/3 of its present age. Observations from ground-based and space-based instruments reveal it as one of the brightest sources of X-ray light known among galaxy clusters. The X-ray emission is produced by the intracluster gas, which is heated to tens of millions of degrees and fills the region between the galaxies. This hot atmosphere outweighs all the stars within the member galaxies, a feature typical of massive clusters, but in Phoenix the central concentration is unusual. The density of the gas is high and its cooling time is short, which means that the gas can radiate away its energy and lower its temperature more quickly than in most other clusters. In many systems, some form of heating offsets this cooling. Yet in Phoenix, the core remains bright and compact, marking it as exceptional. The cluster's total mass is measured to be several million billion times that of the Sun. This value comes from a combination of techniques including X-ray measurements of the hot gas, the motions of the galaxies bound within the cluster, and the gravitational lensing of background galaxies whose light is deflected by the cluster's gravity. Each of these methods gives an independent view of the total mass, and together they indicate that Phoenix is among the most massive clusters known. The spread of galaxies within the cluster reflects this deep potential well. Hundreds of galaxies orbit within it, each a vast island of stars. They range from small dwarfs to large spirals and massive ellipticals. When imaged with optical telescopes, the population is dense and crowded near the center, consistent with the gravitational pull of the cluster core. Beyond its population of galaxies, Phoenix shows remarkable levels of star formation in the central regions. This is unusual for a cluster of its mass and age. In many other clusters, the dense central galaxy forms stars at only modest rates, because the inflow of cooling gas is balanced by outflows from central engines that inject energy back into the medium. In Phoenix, the rate of new star formation is far higher, producing hundreds of solar masses of new stars each year. The light from these young stars adds to the brightness of the central region and sets the cluster apart from the more quiescent systems. The process is directly linked to the cooling of the intracluster gas, which provides the raw material for star birth. The presence of both intense cooling and vigorous star formation has drawn significant attention to Phoenix, as it represents a rare case where the feedback process is common, in other clusters appear less effective. In images that combine different wavelengths, the Phoenix cluster shows multiple layers of structure. The X-ray view outlines the hot atmosphere, symmetric and luminous, centered on the deepest part of the potential. The optical images reveal the swarming population of galaxies. Ultraviolet data highlight the regions of active star formation concentrated toward the core. Radio maps show extended emission associated with outflows from the central galaxy. Together, these datasets describe a system that is not only massive but also active, with gas-cooling stars forming and energy flowing outward from the core. The combination of these phenomena in a single cluster makes it a valuable laboratory for studying the interplay of cooling and heating in dense cosmic environments. The sheer brightness of Phoenix in X-rays allows astronomers to trace the profile of the intracluster medium in detail. The gas temperature declines toward the center, and the density increases, producing the strong central emission. The total X-ray luminosity of Phoenix exceeds that of most clusters, known placing it at the extreme end of the distribution. This alone makes it a target for repeated study, since rare systems often reveal processes that are less visible in the general population. The cooling rate of the gas, if unopposed, would be enough to fuel vast amounts of star formation. Observations show that such star formation is indeed present, though not at the maximum rate predicted, suggesting that some level of energy input still moderates the inflow. When considering the cluster in its cosmic context, it represents a mature node in the web of large-scale structure. It is not a newly formed system, but rather the product of billions of years of accretion and merging. Its current mass places it among the most extreme examples of gravitational clustering in the observable universe. Such clusters are rare, but their study is essential for understanding how matter assembles over time. The Phoenix cluster demonstrates that even in the later universe, extreme cooling and star formation can occur in environments where, by comparison, most other clusters have long since reached a more quiescent balance. The environment of Phoenix is also important for understanding how galaxies evolve inside massive clusters. The dense atmosphere of hot gas exerts pressure on galaxies as they move, stripping away their own supplies of cold gas. This process suppresses star formation in many members, leaving them as red, older stellar populations. Yet the central galaxy, immersed in the highest density of the intra-cluster medium, paradoxically forms stars at an accelerated rate. This contrast highlights the unique conditions at the core and raises questions about the balance of cooling and heating that governs the fate of such galaxies. The scale of the Phoenix cluster emphasizes the link between small-scale processes and large-scale environments. Energy released near the core can affect gas across millions of light-years. At the same time, the overall mass and gravitational field of the cluster dictate the confinement of that gas and the pressure on galaxies. Phoenix, by its sheer brightness and unusual levels of activity, demonstrates this connection in sharp relief. It stands as a reminder that the processes shaping stars and galaxies cannot be separated from the larger structures in which they occur. The dense core, the luminous X-ray atmosphere, the vigorous star formation, and the outflows observed in radio light together paint a picture of a cluster operating at the edge of known extremes, where the universe's largest bound structures reveal both the balance and the tension between gravity cooling and energy release. The most striking feature of the Phoenix cluster beyond its mass and galaxy content is the hot intracluster gas that fills the space between galaxies. This medium is not visible to the human eye, but it dominates the baryonic or ordinary matter content of the cluster. The gas is heated to tens of millions of degrees, and at those temperatures it does not emit visible light, but shines strongly in the X-ray band. Observatories that are able to detect high-energy photons such as the Chandra X-ray Observatory and XMM Newton have revealed the detailed structure of this atmosphere. It is diffuse compared to the density of air on Earth, yet it extends over millions of light-years, and its total mass exceeds that contained in all the stars of the cluster's galaxies combined. It is this medium that records the history of energy exchange within the cluster and provides the fuel for further star formation when conditions allow cooling to progress. The intracluster gas in Phoenix is unusually dense in its central region. In many clusters, the gas density toward the center is moderated by energy released from central engines that prevent runaway cooling. In Phoenix, the cooling proceeds more strongly, producing a luminous X-ray core. The gas radiates energy and loses heat, and as it does so, it should flow inward, potentially fueling star formation in the central galaxy. Observations of Phoenix indicate that a substantial fraction of this expected inflow does indeed reach the core, where new stars are forming at rates much higher than in typical cluster centers. This connection between the cooling of hot gas and the creation of new stars provides direct evidence of the cycle of matter in such environments. The hot gas cools, flows inward, forms stars, and over time the products of those stars, stellar winds and supernova explosions, can return energy and heavy elements back into the surrounding medium. The temperature profile of the intracluster gas is a key diagnostic of the physical state of the cluster. In Phoenix, the outer regions of the atmosphere remain very hot, but the temperature decreases steadily toward the core. This decline marks the cooling of gas as it radiates X-rays. The radial change in temperature is steeper than in many other clusters, highlighting the unusual efficiency of cooling in Phoenix. The density profile also increases sharply toward the center, which is consistent with the brightness of the core observed in X-ray images. By combining measurements of brightness and spectrum, astronomers can derive both the density and temperature at different radii, and from these infer the total mass required to hold the gas in equilibrium. In Phoenix, these analyses confirm the presence of a massive cluster halo dominated by dark matter. Cooling of gas on such large scales is expected to lead to inflows sometimes referred to as cooling flows. In earlier decades, simple models predicted enormous rates of gas condensation in cluster cores enough to form thousands of solar masses of new stars per year. Observations, however, showed that such extreme star formation was not occurring in most systems, leading to the conclusion that some form of heating, usually attributed to feedback from central black holes, must offset much of the cooling. Phoenix is remarkable because it appears closer to the classical picture, with cooling leading to vigorous star formation at hundreds of solar masses per year. This does not mean that feedback is absent, but rather that in this case it has not fully balanced the radiative losses of the gas. The result is a luminous X-ray core and an actively star-forming central galaxy, both rare among clusters of this scale. The intracluster medium also contains traces of elements heavier than hydrogen and helium, often referred to as metals in astrophysical terminology. These elements are produced in stars and distributed into the surrounding space by stellar winds and supernova explosions. Over billions of years, they are mixed into the intracluster gas. Observations of Phoenix show enriched metallicity in its atmosphere, evidence of many generations of star formation and stellar death, contributing material to the cluster environment. The distribution of these elements provides information on how gas has been stirred, redistributed, and enriched across cosmic time. It also influences the cooling properties of the gas, since heavier elements emit radiation more efficiently at certain temperatures. The presence of hot gas at such extreme temperatures implies a long history of heating as well as cooling. During cluster mergers, gravitational energy is converted into heat, raising the temperature of the gas. Shock fronts propagate across millions of light years, compressing and heating the medium. In addition, outflows from central galaxies and their black holes can inject energy in the form of jets or winds. All of these processes contribute to maintaining the high temperatures observed. Yet in Phoenix, the balance tips toward cooling in the core, showing that despite the vast energy input from mergers and central activity, radiation can still dominate in particular regions. This delicate balance between heating and cooling is one of the central themes in cluster astrophysics, and Phoenix provides a vivid case where the interplay is at its most visible. The study of intracluster gas also informs cosmology. Because the gas mass is a large fraction of the total baryonic mass of the universe, measurements of gas fractions in clusters can be compared with predictions from cosmological models. Phoenix, with its enormous gas reservoir, adds to the statistical sample needed to test such models. Its brightness makes it a key data point, and its unusual core conditions mark it as an outlier worth close attention. The intracluster medium in Phoenix demonstrates both the general principles that apply to clusters and the unique conditions that can arise in particular systems. Images of Phoenix in X-rays reveal a smooth outer structure with a luminous, sharply peaked center. The smoothness indicates a system not currently undergoing a major merger, though past interactions have undoubtedly shaped its history. The central peak, however, distinguishes it from many others. In projection, the hot gas forms a glowing envelope surrounding the central galaxy and extending outward to the edges of the cluster. Within this envelope, galaxies move along their orbit stripped of their own gas, but bathed in the diffuse atmosphere that dominates the mass budget. The gas is transparent to visible light, so to the eye the galaxies appear to float in darkness, but to X-ray instruments the background is bright, filling the field with diffuse emission. The Phoenix cluster's intracluster medium, by its density, temperature, and cooling properties, defines the system as extraordinary. It is not simply the backdrop against which galaxies evolve, but the active medium that shapes their fate. It regulates star formation, responds to energy input, and carries the signatures of the cluster's growth. By observing it in detail, astronomers gain insight into both the life cycle of galaxies and the broader balance of matter in the universe. The Phoenix cluster, with its massive, luminous, and unusually active atmosphere, remains a central example in the study of cosmic structure, a system where the hot intracluster gas dominates the scene and reveals processes unfolding on scales of millions of light-years. Within the Phoenix cluster, the galaxies themselves form a crowded population, each following its orbit inside the deep gravitational well defined by the total mass of the system. These galaxies are diverse in shape and brightness, ranging from small dwarfs to massive ellipticals and spirals. Observations with optical and infrared telescopes reveal hundreds of members bound together with their density increasing strongly toward the center. The motions of these galaxies provide valuable measurements of the cluster's mass distribution. By studying their velocities, astronomers can determine how much unseen matter is required to hold the system together. In Phoenix, the results confirm the presence of an enormous dark matter halo whose gravity governs the dynamics of the entire cluster. The galaxies in Phoenix are not isolated in quiet space. Each one moves through the hot intracluster medium at speeds of hundreds to more than 1,000 kilometers per second. As they travel, the pressure of the gas strips away their own reservoirs of cold gas, a process known as ram pressure stripping. This removal of star-forming material leads many of the cluster's galaxies to become quenched, meaning that they no longer form new stars at significant rates. Their light becomes dominated by older, redder stars. The population of galaxies and clusters is therefore skewed toward these quiescent systems, and Phoenix is no exception. Yet despite this trend, the cluster's central galaxy stands out with unusually vigorous star formation. This contrast underscores the unique conditions at the cluster's heart compared with its outer members. Images of the Phoenix cluster in visible light display a swarm of galaxies against a dark background. The central region is especially rich with the brightest cluster galaxy dominating the scene. Surrounding it are numerous satellites, some showing distorted shapes as a result of interactions with the dense environment. These interactions include gravitational encounters between galaxies, tidal stripping, and mergers. Over cosmic time, such encounters alter the shapes and internal structures of galaxies. Spirals can lose their delicate arms and evolve into more spheroidal forms. Dwarfs can be disrupted entirely and absorbed by larger neighbors. In Phoenix, where the density of galaxies is high, such processes are efficient. The result is a population shaped by both internal evolution and environmental effects. Beyond their visible starlight, the galaxies contribute to the intracluster medium through outflows and stellar activity. Supernovae enrich the gas with heavy elements, while galactic winds driven by massive stars carry material outward. Over billions of years, these processes have spread metals throughout the cluster, as shown by X-ray observations of the intracluster gas. The stars themselves provide the light by which the galaxies are detected, but their cumulative contribution to the mass budget is minor compared with the hot gas and the dark matter halo. Nevertheless, their distribution offers clues about the cluster's assembly history. In Phoenix, the central concentration of galaxies, together with the smooth appearance of the outer gas, suggests a relatively relaxed system, rather than one currently undergoing a violent merger. The galaxies also serve as tracers of the cluster's gravitational potential through the phenomenon of gravitational lensing. Light from distant background galaxies is deflected by the mass of the cluster, producing arcs and distortions in images. By analysing these features, astronomers can map the total mass both visible and invisible in the cluster. Phoenix produces such lensing features, and they confirm the scale of its mass as one of the largest gravitationally bound systems known. These observations show that the galaxies within Phoenix are not only residents of the cluster, but also tools for probing its mass and structure. While many of the member galaxies have had their star formation suppressed, the central galaxy is extraordinary in the opposite direction. Observations reveal that it is forming stars at a rate of hundreds of solar masses per year, an intensity rarely seen in cluster cores. The fuel for this process comes from the cooling intracluster gas which condenses and flows inward. This central galaxy is not only the brightest in the cluster, but also one of the most luminous galaxies known in the universe, shining across multiple wavelengths, due to its mix of old stars, new stars, and the energy released by its core. In contrast, the satellite galaxies appear dimmer and more passive, illustrating the dual character of the cluster environment. The relationship between the central galaxy and its satellites is complex. Some of the smaller galaxies may eventually merge into the central one, adding to its mass and luminosity. Others will continue to orbit for billions of years, slowly losing their gas to the cluster medium. Their combined population illustrates the range of evolutionary paths galaxies can follow when subject to the dense atmosphere and strong gravity of a massive cluster. Phoenix provides a striking view of these processes in action, with galaxies at different stages of transformation visible in a single field. Infrared observations add another layer of information. They reveal dust-enshrouded star formation in the central galaxy and measure the older stellar populations in satellites. They also confirm the elevated star formation rate in the core. Together with ultraviolet and radio observations, they build a picture of a cluster where galaxy evolution is strongly shaped by environment. The combination of quiescent satellites and a star-bursting central galaxy distinguishes Phoenix from many other clusters of similar mass. The galaxies of Phoenix are also aligned with the cluster's large-scale potential. Their spatial distribution traces the shape of the dark matter halo, which is inferred to be roughly spherical on large scales with some elongation. By mapping this distribution, astronomers can compare it with simulations of structure formation. Phoenix matches expectations for a massive cluster that has grown steadily over billions of years. Its galaxies stripped and transformed are the visible witnesses of this history. The bright central galaxy fed by cooling gas stands as the focal point of the system. By examining the galaxies within Phoenix, one sees the imprint of the cluster environment on cosmic structures that in isolation would evolve differently. Ram pressure stripping mergers, tidal interactions, and the balance between cooling and heating all leave their marks. The Phoenix cluster is not simply a collection of galaxies, but a dynamic ecosystem, where each galaxy interacts with the shared medium and with its neighbours. The result is a population distinct from galaxies found in the field, emphasizing how environment governs fate. In Phoenix, the galaxies reveal both suppression and enhancement of star formation, illustrating the range of outcomes possible within the same system. The galaxies taken together present a complex but coherent view of the cluster as a whole. They confirm the scale of the gravitational potential, enrich the intracluster medium, and show evidence of transformation under environmental forces. In Phoenix, the combined picture is one of extremes quenched satellites, a luminous and active central galaxy, and a distribution that maps the underlying mass. The cluster's galaxies are thus both subjects of transformation and traces of the system that holds them. Their presence adds a critical dimension to the study of Phoenix, connecting the hot gas and dark matter halo to the visible stellar populations that mark the cluster across cosmic time. At the very heart of the Phoenix cluster lies its brightest cluster galaxy, a system so large and luminous that it dominates the center of the gravitational well. This central galaxy is often referred to as the brightest cluster galaxy, or BCG, a class of galaxies found in nearly all massive clusters, but here taken to an extreme. The BCG in Phoenix outshines the rest of the cluster's population, stretching across hundreds of thousands of light-years and containing trillions of stars. It is not simply the largest member, but also the one most directly influenced by the inflow of cooling gas from the intracluster medium. The galaxy is enveloped by streams of hot gas dust and young stars, evidence of an active environment unlike the relative quiescence of most cluster cores. Observations across multiple wavelengths show that this central galaxy is forming stars at a rate of several hundred solar masses per year. Such a starburst is highly unusual in a cluster environment, where cooling gas is often offset by heating from the active nucleus suppressing star formation. In Phoenix, the balance is different, and the central galaxy glows with intense ultraviolet light from young stars, strong infrared emission from dust heated by that star formation, and bright optical light from both new and old stellar populations. The result is one of the most luminous galaxies known visible across the electromagnetic spectrum. Its radiance is not merely a product of its stellar mass, but also of the continuous replenishment of new stars being born from the cooling core of the cluster atmosphere. The structure of the galaxy is complex. Optical images show extended filaments of gas stretching tens of thousands of light-years from the center. These filaments are visible in the light of ionized hydrogen, a sign of gas cooling and condensing out of the hot medium. They weave outward from the core tracing channels where material is funneled inward to feed both star formation and, at the very center, the central black hole. The combination of starburst and nuclear activity makes the BCG in Phoenix a rare hybrid simultaneously undergoing processes that in most clusters are mutually exclusive. Instead of a quenched core with subdued star formation, Phoenix presents a core ablaze with stellar birth and high-energy phenomena. The size of the BCG is itself striking. Its envelope extends over 300,000 light-years, much larger than the Milky Way. Within this span are billions of solar masses in stars organized into a smooth, spheroidal distribution with a dense core. Surrounding the galaxy are streams of stars pulled from smaller galaxies that have merged into the central system. Over billions of years, the BCG has grown by cannibalizing its neighbors, a process common in cluster centers, but especially efficient here due to the density of galaxies and the depth of the potential well. The stellar halo of the central galaxy contains the remnants of many mergers, while its core hosts the ongoing activity driven by cooling gas. Spectroscopic observations reveal both old stellar populations with ages of many billions of years and young stars formed in the past few 100 million years. This mixture indicates a galaxy that has not only accumulated mass through mergers, but also rejuvenated itself through recent starbursts. The young stars are concentrated along filaments and in clumps near the center, while the older population forms a diffuse background. Together they create a layered record of the galaxy's history, from its ancient foundation to its current period of activity. The central galaxy's brightness is not confined to starlight. Radio observations detect emission from jets launched by the supermassive black hole at its core, indicating that the galaxy hosts an active galactic nucleus. These jets, while faint compared with those of some powerful quasars, extend tens of thousands of light years into the intracluster medium interacting with the surrounding gas. The coexistence of strong star formation and nuclear activity makes the Phoenix BCG a key system for understanding how gas-cooling starburst and black hole feedback can operate together. Normally, the energy released by the black hole is enough to suppress star formation, but here the suppression is incomplete, leaving both processes visible. Infrared observations with the Spitzer Space Telescope and later with the Herschel Space Observatory confirm the enormous dust content of the central galaxy. Dust absorbs ultraviolet light from young stars and re-emits it in the infrared, providing a measure of the total star formation rate. In Phoenix, the infrared luminosity is extreme, consistent with hundreds of solar masses of stars forming each year. This makes the galaxy a luminous infrared galaxy, a rare category in the cluster environment. The dust itself is supplied by supernovae and evolved stars and is preserved in part by the continuous inflow of fresh gas from the cluster atmosphere. Ultraviolet images from the Hubble Space Telescope show knots and filaments of star formation spread across the central tens of thousands of light years. These bright regions trace the most recent generation of stars. Their distribution indicates that star formation is not confined to the nucleus, but spread over extended filaments following the paths of cooling gas. Such structures are seen in some other cool core clusters, but rarely at this level of activity. Phoenix represents the upper end of the distribution, where both the scale and intensity of star formation are maximized. The central galaxy also plays a key role in redistributing energy within the cluster. While it draws in cooling gas, it also drives outflows powered by its active nucleus. These outflows carve cavities in the hot intracluster medium and inflate bubbles filled with relativistic particles. In Phoenix, these cavities are visible in X-ray images, though they are less dominant than in clusters where feedback fully balances cooling. The simultaneous presence of inflows fueling star formation and outflows carving cavities highlights the dynamic balance at work. The central galaxy sits at the nexus of this cycle, mediating between the cluster atmosphere and the black hole at its core. The extreme nature of the BCG in Phoenix has made it the subject of numerous detailed studies. It challenges standard models of cluster cores, showing that under some conditions, the cooling of hot gas can proceed to fuel both massive starbursts and active nuclei simultaneously. The luminous filaments, the high star formation rate, the extended halo, and the evidence of mergers all combine to make this galaxy a unique example of how central cluster galaxies can evolve. It demonstrates that even in environments dominated by suppression and quiescence, exceptions exist where activity reaches remarkable levels. In the Phoenix cluster, the brightest cluster galaxy embodies the convergence of many cosmic processes. It is a record of mergers, a host of extreme star formation, a source of dust and filaments, and the site of nuclear outflows. It is far larger and more luminous than the Milky Way, and it illustrates the extraordinary conditions that can occur in the centers of massive clusters. By focusing on this galaxy, astronomers see not only the outcome of billions of years of growth, but also the present-day interplay of cooling star formation and feedback, all unfolding at the core of one of the universe's most remarkable systems. The evidence that the brightest cluster galaxy in Phoenix is anchored by a supermassive black hole comes from multiple observational signatures. In almost all large galaxies, a black hole resides at the center, with a mass that scales roughly with the total mass of the galaxy's bulge. For galaxies as large as the Phoenix Central Galaxy, This relation predicts a black hole of billions of solar masses. The intense activity seen in the core, including radio jets, X-ray cavities, and high-energy emission, indicates that the central black hole is not quiescent, but actively accreting material. In Phoenix, the connection between the cooling of the intracluster medium and the activity of the black hole is especially clear, for the inflowing gas that fuels star formation can also feed the nucleus. Observations in the X-ray band reveal excess energy in the central tens of thousands of light-years energy that cannot be accounted for solely by stars or gas cooling. Instead, it is consistent with heating produced by an active galactic nucleus, where gas falling toward the black hole releases gravitational energy as radiation and particles. Radio data show extended lobes emerging from the center, a classic signature of jets powered by a central engine. These lobes extend tens of thousands of light-years and interact directly with the intracluster gas-inflating cavities that are visible as depressions in X-ray brightness. The presence of such features is one of the strongest indicators that a black hole is actively injecting energy into its environment. The optical spectrum of the central galaxy further supports the presence of an active nucleus. Emission lines from ionized gas broadened by high velocities trace material heated and accelerated near the black hole. The ionization levels require a powerful source of high-energy photons consistent with the accretion of matter into the deep gravitational potential of a supermassive black hole. Combined with ultraviolet and infrared data, these features point to a central engine releasing energy across the electromagnetic spectrum. The coexistence of this active nucleus with high rates of star formation is rare, yet in Phoenix both processes are observed at extreme levels. The interaction of the black hole with its environment is seen most directly in the cavities carved into the intracluster medium. These are regions where the hot gas has been displaced by bubbles, inflated with relativistic particles and magnetic fields carried outward by jets. In X-ray images, the cavities appear as darker regions surrounded by brighter rims, indicating that gas has been pushed aside. The energy required to create such structures is enormous, corresponding to the output of the black hole over tens of millions of years. In Phoenix, these cavities are smaller compared with the total cooling luminosity of the cluster, which explains why cooling and star formation remain vigorous. Nonetheless, their presence confirms that the central black hole is active and capable of influencing gas on scales far beyond the galaxy itself. The balance between inflows and outflows is critical. Cooling of the intercluster medium drives gas inward toward the center, while feedback from the black hole pushes outward. In most clusters, this balance suppresses runaway star formation. In Phoenix, the feedback is not strong enough to offset cooling completely, allowing both inflows and outflows to coexist. This intermediate state gives astronomers a rare opportunity to study the interplay of processes in real time. The black hole is seen both as a source of regulation and as a participant in ongoing growth, a dynamic that challenges simplified models of cluster evolution. Direct measurement of the black hole's mass in Phoenix is beyond current resolution given its great distance. Instead, astronomers rely on indirect methods. The correlation between galaxy bulge mass and black hole mass provides one estimate. For a central galaxy as massive as that in Phoenix, the predicted black hole mass could be tens of billions of solar masses. The energy required to inflate the observed cavities provides another estimate, since the black hole must have accreted enough mass to power the outflows. The luminosity of the active nucleus once corrected for obscuration offers additional constraints. Taken together, these lines of evidence point to one of the most massive black holes known, though the exact value remains uncertain. The behavior of the central gas also supports the presence of a black hole. Filaments of ionized gas stretching tens of thousands of light years are aligned with the direction of jets, suggesting that outflows have influenced their structure. At the same time, cold molecular gas has been detected in large quantities, providing fuel for both star formation and accretion. The coexistence of cold, warm and hot gas phases in the central region reflects the complex cycle of matter around the black hole. Cooling gas condenses and flows inward, star formation consumes part of it, and feedback from the nucleus heats and displaces another fraction. This cycle operates continuously, shaping the evolution of the galaxy and its environment. The scale of influence of the black hole in Phoenix is remarkable. Though the event horizon itself would be only a few 100 billion kilometers across, even for the largest possible mass, the effects of its activity extend to hundreds of thousands of light years. The jets and cavities reach into the intracluster medium, altering gas that outweighs all the stars in the galaxy. This illustrates how a compact object at the center can affect a volume millions of times larger than its immediate size. The Phoenix cluster is therefore not just an environment for galaxies and gas, but also a stage on which the power of a black hole is expressed at cosmic scales. Astronomers continue to monitor the Phoenix central galaxy across the spectrum. New observations at millimeter wavelengths have revealed large amounts of cold molecular gas concentrated near the nucleus. This gas provides the reservoir that sustains both star formation and black hole growth. Measurements of its dynamics suggest complex motions with inflows feeding the center and outflows driven by feedback. The balance between these processes determines whether the black hole continues to grow rapidly, whether star formation remains intense, and whether the intracluster medium is significantly heated. Phoenix offers an active laboratory for testing these interactions under extreme conditions. The evidence for a central engine in Phoenix is thus overwhelming. X-ray cavities, radio jets, optical emission lines, infrared dust emission, ultraviolet starburst light and molecular gas dynamics all converge on the conclusion that a supermassive black hole lies at the heart of the cluster's brightest galaxy. Its activity is both a response to cooling inflows and a cause of heating. Outflows a feedback cycle visible on scales from tens of parsecs to millions of light years. While the precise mass remains uncertain, the scale of its influence leaves little doubt that the black hole is among the largest in the known universe, a hidden object whose presence is revealed only by the vast structures it creates in its environment. When gas falls toward a supermassive black hole, it does not plunge directly inward. Instead, it settles into an accretion structure, a rotating disk or flow of matter that gradually spirals closer under the influence of friction and gravity. In the case of the central galaxy in the Phoenix cluster, the large amounts of cooling gas detected in multiple phases suggest that the black hole is supplied by a steady inflow. This accretion process converts gravitational potential energy into radiation and into mechanical energy carried by outflows. The efficiency of the conversion is high compared with nuclear reactions in stars, making accretion one of the most powerful energy sources in the universe. The presence of luminous emission across the spectrum, the detection of jets, and the displacement of gas in cavities all point to active accretion in Phoenix. The physical conditions in the accretion structure are extreme. Gas temperatures in the inner regions can rise to millions of degrees, while orbital speeds approach a significant fraction of the speed of light. The radiation emerging from these regions is intense and covers a wide range of wavelengths from X-rays to ultraviolet to visible light. The variability of this emission, seen in many active galaxies, is often used to probe the size and structure of the disk. In Phoenix, the distance is too great to resolve the accretion disk directly, but the combination of spectral features and the power required to drive observed outflows confirm its presence. The accretion disk acts as the immediate environment of the black hole, mediating between the inflow of matter from the galaxy and the release of energy into the cluster. Around the disk, a corona of hot electrons can scatter photons to higher energies, producing X-ray emission. This component is common in active galactic nuclei and is likely present in Phoenix as well. The X-rays observed from the core include both thermal radiation from hot gas and non-thermal components from the active nucleus. By separating these contributions, astronomers can estimate the relative power of the accretion flow and the cooling intracluster medium. The fact that both are luminous indicates a system where gas cooling star formation and black hole accretion are all proceeding at substantial rates. The inflow of gas toward the disk is not smooth but clumpy and turbulent. Cold molecular gas detected in Phoenix is arranged in filaments that may rain down toward the center. These filaments extend tens of thousands of light years and contain billions of solar masses of material. As they move inward, they fragment and collapse, some forming stars, others feeding the black hole. Observations with millimeter and sub-millimeter telescopes have traced these structures in carbon monoxide emission, confirming their mass and dynamics. The presence of such large reservoirs ensures that the accretion disk can remain active over long timescales, sustaining both the starburst and the nucleus. The efficiency of accretion determines the energy output. For a given rate of mass inflow, a fraction is converted into radiation and mechanical energy. In Phoenix, estimates of the star formation rate and the power of the jets imply that significant amounts of gas are being funneled toward the center. Even if only a small percentage of this material reaches the black hole, the resulting luminosity is sufficient to produce the observed activity. The rest may form stars or remain in extended filaments. This division of gas between different pathways is a key question in understanding how central cluster galaxies evolve. Magnetic fields play an important role in the accretion process. They mediate the transport of angular momentum, allowing matter to spiral inward. They also channel outflows and jets, focusing energy into narrow beams. In simulations of black hole accretion, magnetic fields thread the disk and launch winds that carry away part of the inflowing gas. In Phoenix, the presence of radio jets implies that such magnetically driven processes are operating. The coupling of accretion physics on scales of light hours to structures on scales of hundreds of thousands of light years is one of the remarkable aspects of black hole systems. The radiation from the accretion disk and its corona interacts with surrounding gas, ionizing it and producing characteristic emission lines. In Phoenix, optical spectra show strong lines from ionized oxygen, nitrogen, and hydrogen, consistent with illumination by an active nucleus. These lines broaden because the gas is moving at thousands of kilometers per second under the influence of the black hole's gravity. The widths of these lines provide indirect estimates of the central mass, though at Phoenix's distance the uncertainties are large. Still, the data confirm that the central object is massive enough to dominate the dynamics of gas in its immediate vicinity. The interplay of accretion and feedback is evident in the balance of cooling and heating in the cluster core. Gas cools and flows inward, forming the reservoir that supplies the disk. The disk converts part of this mass into radiation and jets, which in turn heat and displace surrounding gas. In Phoenix, cooling dominates sufficiently to allow massive star formation, but feedback is also present, visible in the cavities and jets. This balance may shift over cosmic time, with periods of stronger feedback, reducing cooling followed by intervals when cooling resumes. The current state of Phoenix shows the system during a phase when cooling is vigorous, feeding both stars and the black hole simultaneously. The scale of the accretion process is small compared with the cluster, but central to its evolution. The event horizon of the black hole may span only light hours to light days, yet the energy released there shapes gas flows over millions of light years. The accretion disk, though invisible directly, is inferred from its consequences across a vast range of scales. Phoenix exemplifies how processes at the smallest accessible lengths in astrophysics can govern phenomena at the largest. The link between a disk of hot gas orbiting a compact object and the star formation history of an entire galaxy cluster illustrates the depth of these connections. Future observations with more sensitive instruments may resolve even finer details of the accretion process in Phoenix. High-resolution X-ray spectroscopy will trace the motions and ionization states of gas near the core. Millimeter interferometry will map the inflowing filaments with greater clarity. Together, these approaches aim to reveal exactly how gas makes the final journey from large-scale filaments down to the black hole's accretion disk. Until then, the indirect evidence from emission jets and cavities provides a compelling picture of an active accretion structure fueling one of the most massive black holes in the universe. From the accretion disk of the Phoenix Central Galaxy emerge narrow, powerful jets of plasma streams of matter, accelerated to nearly the speed of light, and focused by magnetic fields into beams that travel tens of thousands of light years into the surrounding intracluster medium. These jets are one of the most visible consequences of active black hole accretion and provide direct evidence that energy released near the event horizon can influence regions vastly larger than the disk itself. In Phoenix, the jets are detected in radio wavelengths, where synchrotron emission from relativistic electrons spiraling around magnetic fields produces bright elongated structures. The alignment and extent of these features confirm that the black hole is driving outflows that couple to the environment on scales comparable to the size of galaxies. The jets of Phoenix interact with the hot intracluster gas inflating lobes and cavities that displace material and create observable depressions in X-ray images. These cavities, though smaller, relative to the overall cluster compared with some other systems, testify to repeated episodes of jet activity. Each outburst carries energy sufficient to heat surrounding gas and to alter its distribution. The displaced regions eventually refill as gas flows around them, but the evidence of past activity remains imprinted in the X-ray surface brightness. By measuring the size and pressure of these cavities, astronomers can estimate the total mechanical energy injected by the black hole. In Phoenix, the values are high, but still fall short of fully offsetting the rapid cooling observed in the core. This imbalance explains why star formation remains vigorous, with cooling gas slipping past the regulation of jet heating. The dynamics of the jets themselves are governed by both the properties of the accretion disk and the surrounding medium. Magnetic fields anchored in the rotating disk are thought to twist and accelerate plasma, launching it outward in collimated beams. Once expelled, the jets propagate through the intracluster medium, sometimes remaining narrow, sometimes broadening into lobes as they slow and spread. In Phoenix, the jets appear relatively compact compared with those in some giant radio galaxies, but their impact is nonetheless significant. They mark the channel through which the black hole communicates with the cluster, transmitting energy from scales of light hours to scales of hundreds of thousands of light years. The composition of the jets is still uncertain. They may contain electrons and positrons, or electrons and protons, or a mix of both. Whatever their makeup, they carry relativistic particles and magnetic fields that radiate as they interact with the environment. The synchrotron emission reveals the presence of these particles and provides information about their energies and lifetimes. In Phoenix, the radio maps show structures aligned with the central nucleus, indicating a direct connection to ongoing accretion. The fading of emission away from the center shows that particles lose energy as they travel either through radiation or through interactions with the intracluster medium. The feedback effect of jets is a central theme in galaxy cluster astrophysics. In many clusters, jet heating balances radiative cooling of the core, preventing massive starbursts. The Phoenix cluster is unusual because this balance is incomplete. The jets have carved cavities, but the cooling rate of the core exceeds the heating rate, leaving room for large-scale star formation. This situation may represent a temporary phase in a long cycle of activity. Jets may strengthen in the future and suppress cooling more effectively, or they may have been stronger in the past and allowed the current state by declining in power. Either way, the Phoenix system captures a moment when both feedback and cooling are active, offering insight into how regulation operates over time. The cavities inflated by jets are not empty voids, but filled with relativistic plasma. Their buoyant rise through the intracluster medium stirs the surrounding gas, driving turbulence and mixing. As the cavities move outward, they can transport energy far from the center. The rims around the cavities often show compressed gas heated and brightened by the displacement. In Phoenix, such rims are visible though less pronounced than in some classic examples like the Perseus cluster. Still, their presence demonstrates that the black hole's influence extends beyond the galaxy itself into the shared atmosphere of the cluster. Jets can also trigger star formation under certain conditions. By compressing gas as they plow through the medium, they may promote collapse in some regions. In Phoenix, the presence of star-forming filaments aligned with jet directions hints at such interactions, though the dominant source of fuel for stars remains the cooling inflow from the intracluster medium. The combined action of compression, cooling, and turbulence shapes the distribution of new stars in the central galaxy. Observations of ultraviolet knots along filaments suggest that feedback does not merely suppress star formation, but can also help structure it. The lifetime of jets in Phoenix is measured in tens of millions of years, consistent with typical active galactic nucleus cycles. Over cosmic time, many such episodes may occur, each inflating new cavities and injecting new energy. The current jets are only the most recent expression of a process that has likely operated for billions of years. Their cumulative effect influences the long-term evolution of the cluster core, preventing unchecked cooling, while allowing bursts of star formation. In Phoenix, the cycle appears to be in a phase of relatively weak feedback, with cooling temporarily dominant. Understanding jets also informs the study of cosmic magnetism. The magnetic fields carried outward in plasma lobes contribute to the magnetization of the intracluster medium. Over billions of years, such processes may account for the pervasive magnetic fields observed across clusters. Phoenix, with its active nucleus and multiple cavities, adds to the evidence that black holes are key sources of magnetization on large scales. The magnetic pressure in the lobes also helps support them against collapse, extending their lifetime and impact. The morphology of jets provides clues to the orientation and spin of the central black hole. In Phoenix, the jets are roughly symmetric, suggesting a stable orientation over recent timescales. This stability indicates that the accretion disk has maintained a consistent axis, possibly aligned with the black hole's spin. In other systems where the accretion flow changes direction, jets can precess or bend, leaving complex structures. Phoenix does not show strong bending, though smaller symmetries reflect the influence of surrounding gas. Such observations connect the smallest scale of black hole spin with the larger structures of the cluster atmosphere. The jets of Phoenix are not the most powerful known, but their importance lies in their context. They exist within one of the most massive clusters, interact with an unusually bright and cooling core, and coexist with extraordinary levels of star formation. Their presence confirms the role of black holes as engines capable of shaping galaxy clusters, while their relative weakness compared with cooling explains the unique state of Phoenix. Without jets, cooling might proceed unchecked, while with stronger jets, star formation might be quenched. The present balance produces a rare system where both processes are visible, highlighting the complexity of feedback in the universe's largest bound structures. In Phoenix, the narrow jets emerging from a tiny region near the black hole extend to influence gas weighing more than 1 trillion times the mass of the Sun. They demonstrate the reach of black hole feedback, the bridge between microphysical processes in accretion disks and the macroscopic state of cluster atmospheres. By tracing these outflows, astronomers see how energy travels across scales, shaping galaxies, clusters, and cosmic structures over time. Beyond the narrow jets that extend from the active nucleus of the Phoenix Central Galaxy lie even larger structures in the intra-cluster medium, vast cavities carved into the hot gas. These cavities appear in X-ray images as depressions in surface brightness regions where the normal glow of hot plasma is absent, because it has been pushed aside by outbursts from the black hole. In Phoenix, these features provide clear evidence of mechanical feedback operating over tens of millions of years. They are the imprints left by repeated cycles of jet activity, each episode inflating bubbles of relativistic plasma that rise buoyantly through the surrounding gas. The cavities are not empty, but filled with non-thermal particles and magnetic fields, remnants of the energy released near the black hole. Measurements of cavity size and the pressure of the surrounding medium allow astronomers to calculate the energy required to create them. This so-called cavity power is a measure of the average mechanical output of the active galactic nucleus over time. In Phoenix, the cavity power is large, consistent with significant energy release, yet when compared with the radiative losses of the cluster's core, it falls short of fully counteracting cooling. This mismatch explains why Phoenix supports both luminous X-ray emission from cooling gas and intense star formation in the central galaxy. The cavities show that the black hole is active and influential, but not dominant enough to completely regulate the flow of energy. The shapes of cavities in Phoenix are relatively symmetric, aligned with the axis of radio jets. They extend tens of thousands of light years from the center, displacing gas in roughly opposite directions. Their buoyant rise creates circulation in the intracluster medium, stirring turbulence and mixing metals produced by stars. Over time, these cavities may detach and drift outward, replaced by new ones from subsequent jet activity. In this way, the black hole repeatedly imprints itself on the cluster, leaving a stratified record of past outbursts. X-ray observations have identified multiple pairs of cavities in some clusters, corresponding to episodic cycles of activity. Phoenix shows evidence for at least one major cycle, with possible hints of older structures farther out. The rims of cavities often appear brighter in X-rays where displaced gas is compressed and heated. These rims outline the boundaries of bubbles and provide additional constraints on their age and energy. In Phoenix, the rims are less pronounced than in some nearby clusters, partly due to distance and resolution limits. Still, careful analysis shows enhancements that confirm compression. The absence of strong shock fronts indicates that the cavities were inflated gently with subsonic expansion rather than explosive ejection. This gentle mode of feedback is common in clusters where black holes release energy steadily over long periods rather than in sudden bursts. The existence of cavities has broad implications. They demonstrate that black holes can affect gas on scales of hundreds of thousands of light years. They also serve as calorimeters measuring how much energy has been deposited into the cluster atmosphere. In Phoenix, the balance between cavity power and radiative cooling defines the system's state. Cooling is not suppressed, but neither is it uncontrolled. Instead, both processes operate with inflows forming stars and feeding the nucleus, while outflows carve cavities and stir the medium. The result is a cluster core in dynamic equilibrium maintained not by stasis but by continuous exchange. Radio observations complement the X-ray view by filling the cavities with emission from relativistic electrons. In Phoenix, the radio lobes align with the X-ray depressions, confirming that they are indeed bubbles of plasma inflated by jets. The synchrotron emission provides information about particle energies and magnetic fields. The fading of radio brightness away from the center reflects energy losses as particles radiate and age. These observations help constrain the age of cavities, which in Phoenix are estimated to be tens of millions of years old. Such timescales are typical of feedback cycles, showing that black hole activity is recurrent rather than constant. The Phoenix cavities also illustrate how feedback can spread metals and heat through the cluster atmosphere. As bubbles rise, they entrain cooler gas and drag it outward, mixing it with hotter surroundings. They also generate turbulence that redistributes energy. This mixing helps explain the broad distribution of heavy elements seen in intracluster gas. Stars in galaxies produce metals which are ejected by supernovae and stellar winds. Without mixing, they would remain concentrated near galaxies, but in reality they're found throughout cluster atmospheres. Cavities are one of the mechanisms responsible for this spread. The morphology of cavities reveals the orientation and stability of jet activity. In Phoenix, the roughly symmetric arrangement suggests a consistent jet axis over recent cycles. In some clusters, precession or changes in accretion flow cause cavities to appear at different angles, but Phoenix does not show strong evidence for such variation. This stability may reflect a steady supply of gas aligned with the black hole's spin, maintaining a fixed orientation over tens of millions of years. The alignment also contributes to the coherent structure of filaments seen in the central galaxy, which appear influenced by outflows along the same axis. One of the enduring questions is why Phoenix remains so active in star formation, despite the presence of cavities. The answer lies in the relative magnitudes of cooling and heating. The radiative cooling rate of the core is among the highest known, and while cavity power is significant, it does not fully offset this loss. As a result, cold gas continues to form and flow inward, fueling both stars and the black hole. Phoenix thus provides a snapshot of a system where feedback is present but insufficient, allowing a starburst to coexist with an active nucleus. This contrasts with many other clusters, where cavities alone appear to balance cooling, leaving quiescent cores with little new star formation. The cavities in Phoenix are not only scientific markers, but also visual reminders of the scale of black hole influence. A region only light hours across can displace gas over distances measured in tens of thousands of light years. The bubbles inflated by this process carry energy equivalent to billions of supernovae, yet they remain secondary to the overall cooling luminosity of the cluster. This disparity underscores the exceptional state of Phoenix, where even one of the universe's most powerful engines cannot fully stem the flow of cooling gas. Over time, the cavities will rise farther from the center, dispersing into the outer cluster. New cavities may replace them, sustaining the cycle. Each episode adds to the cumulative impact of feedback, ensuring that even if cooling dominates for a time, heating is never absent. The Phoenix cluster exemplifies this balance, with cavities serving as the clearest markers of black hole activity, imprinted on the vast atmosphere of hot gas. Their study allows astronomers to measure past energy output and to understand how clusters maintain a delicate equilibrium over billions of years, The regulation of cooling and star formation in galaxy clusters depends on a process known as feedback, the cycle in which energy released by a central black hole counteracts the radiative losses of the intracluster medium. In most massive clusters, the feedback appears to achieve a rough balance, suppressing the runaway cooling flows predicted by simple models and maintaining cores where star formation is relatively modest. The Phoenix cluster is exceptional because this balance is shifted. The energy released by the black hole, though significant, has not fully offset the cooling of gas in the dense core, leaving conditions where inflows proceed and new stars form at extraordinary rates. Understanding this interplay is essential for interpreting the state of Phoenix and its difference from more typical clusters. The cooling of gas in a cluster core is driven by the emission of X-rays. As hot gas radiates energy, it loses pressure support and flows inward. If unchecked, this process would lead to condensation of vast amounts of cold gas and star formation far exceeding observed levels. The discovery of feedback solved this puzzle. Energy, released by accretion onto central black holes, is deposited into the gas through jets, cavity shocks and turbulence, reducing the net cooling rate. Observations across many clusters support this view, showing a correlation between cavity power and radiative losses. In Phoenix, however, the cooling rate remains among the highest known, while cavity power is comparatively lower. The feedback cycle is active but incomplete, leaving both cooling and heating visible in strong measure. The result is a central galaxy undergoing rapid growth. Its star formation rate is hundreds of times higher than in most brightest cluster galaxies. This starburst consumes part of the inflowing gas while another part continues inward to feed the black hole. The coexistence of high star formation and active nucleus is a rare condition, one that reveals the balance of feedback is not static, but variable over time. Phoenix may be observed during a phase when feedback lags cooling, allowing activity to rise. Over longer timescales, future outbursts may inject more energy and suppress cooling, shifting the balance again. Evidence for this regulation is seen in the multiphase gas of the core. Hot plasma at tens of millions of degrees surrounds the galaxy, but embedded within it are filaments of warm ionized gas and large reservoirs of cold molecular gas. These phases represent the products of cooling condensed from the hot atmosphere. Ultraviolet and optical images reveal filaments of ionized hydrogen stretching tens of thousands of light years. Millimeter observations detect carbon monoxide emission from cold gas amounting to billions of solar masses. This gas provides the direct fuel for both star formation and accretion. Its presence demonstrates that cooling is proceeding at rates unmatched in most clusters. Feedback manifests not only in cavities, but also in turbulence and sound waves that ripple through the intracluster medium. In some nearby clusters, concentric ripples in X-ray images have been interpreted as weak shock or sound waves driven by the periodic inflation of cavities. These waves carry energy outward and help distribute heating across the core. In Phoenix, the distance makes detection of such features more difficult, but indirect evidence of turbulence exists in broadened emission lines and irregular gas structures. This turbulence may slow cooling by mixing hot and cold gas, but again it is not sufficient to halt the process. The balance tips toward cooling, ensuring that new stars and inflows continue. The feedback cycle is therefore a dynamic competition. Gas cools, flows inward, and fuels both stars and the black hole. The black hole releases energy pushing outward through jets and cavities. When feedback is strong, cooling is reduced. When it is weaker, cooling resumes. Phoenix illustrates this cycle in an unusually active phase when feedback is evident but insufficient. This condition helps explain the rarity of such systems. The timescales of imbalance may be short, compared with cosmic history, making Phoenix a brief but revealing state in the life of a cluster. The consequences of this regulation extend to the larger cluster environment. The inflows of gas into the core reduce the central pressure, drawing more material inward from surrounding regions. Outflows and cavities displace and mix gas redistributing energy and metals. The overall structure of the intracluster medium reflects both processes. Phoenix shows a dense peaked core where cooling dominates, surrounded by smoother outer regions shaped by past heating. The coexistence of these signatures demonstrates that feedback does not act as a simple switch, but as a continuous process varying in strength. The study of Phoenix also informs models of galaxy formation. The regulation of gas cooling by black holes is thought to be critical in shaping the most massive galaxies. Without feedback, galaxies in cluster centers would grow too large and bright compared with observations. Feedback provides the necessary check limiting growth and maintaining consistency with data. Phoenix shows that this regulation is not perfect and that exceptions exist where central galaxies do grow rapidly. The existence of such systems provides constraints on the range of feedback efficiency in cosmological simulations. By comparing Phoenix with more typical clusters, astronomers can refine models of how black holes control galaxy evolution. One important measure is the ratio of star formation to cooling rate. In many clusters, the actual star formation is less than 10% of the predicted cooling rate, showing that feedback suppresses most condensation. In Phoenix, the ratio is far higher, with star formation representing a large fraction of the expected inflow. This makes Phoenix an outlier and demonstrates the diversity of outcomes. The system provides a test of whether feedback always enforces suppression, or whether under some conditions cooling can overcome regulation. The answer in Phoenix is clear. Cooling has gained the upper hand, at least temporarily, producing one of the most extreme starbursts seen in the universe today. The feedback cycle also shapes the future of the cluster. If cooling continues unchecked, the central galaxy will accumulate large amounts of new stars and gas, altering its mass and structure. The black hole will grow as well, increasing its ability to release energy in future outbursts. Eventually, feedback may strengthen, quenching star formation and restoring balance. This cyclical view, with phases of activity followed by phases of suppression, provides a framework for interpreting not only Phoenix, but clusters across cosmic time. Phoenix represents a vivid snapshot of the cycle at one extreme, showing both intense cooling and active feedback in progress. By examining Phoenix, astronomers see feedback in action, on scales ranging from the accretion disk to the cluster atmosphere. The system demonstrates how a black hole can regulate its environment not by a single burst, but by repeated cycles of outflows and inflows. The cavities, jets, turbulence, and star formation all record this interaction. The state of Phoenix today may not last, but its study reveals the mechanisms that govern the growth of galaxies and the evolution of clusters. In this way, feedback in Phoenix provides both a unique example and a broader lesson about the balance of forces that shape the larger structures in the universe. Estimating the mass of the central black hole in the Phoenix cluster is one of the most challenging aspects of studying this extraordinary system. At a distance of more than 5 billion light-years, the black hole cannot be measured directly by observing stellar or gas motions as in nearby galaxies. Instead, astronomers rely on indirect methods combining scaling relations, energetic arguments, and comparisons with similar systems. These methods converge on the conclusion that this central black hole must be among the most massive ever discovered, though the exact figure remains uncertain. One approach uses the well-established correlation between the mass of a galaxy's bulge and the mass of its central black hole. This empirical relation has been measured in many nearby galaxies, where black hole masses can be determined from stellar dynamics. In the case of the Phoenix brightest cluster galaxy, the stellar bulge is enormous, containing trillions of solar masses in stars. Extrapolating the scaling relation suggests a black hole mass of tens of billions of solar masses. While uncertainties increase when extending the relation to such extreme systems, the prediction aligns with the extraordinary scale of Phoenix. Another method estimates black hole mass from the power required to inflate observed cavities in the intracluster medium. The mechanical energy of cavities provides a lower bound on the integrated energy output of the black hole. Dividing this energy by a reasonable estimate of accretion efficiency yields a minimum mass that must have been consumed to power the outflows. In Phoenix, the cavities are large enough that the implied black hole mass must be in the multi-billion solar mass range. This approach does not provide a precise number, but supports the idea that the central engine ranks among the heaviest. The luminosity of the active nucleus offers a third line of evidence. When corrected for obscuration, the radiative power can be compared with the theoretical maximum output for a given black hole mass known as the Eddington limit. The Phoenix nucleus radiates strongly across the spectrum, yet appears to be operating below the maximum allowed for a black hole of tens of billions of solar masses. This consistency again points to an enormous central object. If the black hole were significantly less massive, the observed luminosity would approach or exceed the theoretical limit, which is not supported by data. Spectroscopic measurements add further constraints. Emission lines broadened by high velocities indicate gas moving in the gravitational potential of the black hole. In Phoenix, the widths of these lines are large, consistent with motions of thousands of kilometers per second. While the distance makes it difficult to measure line profiles in detail, the observed values match expectations for a massive nucleus. Comparisons with similar active galaxies at closer distances strengthen the case that Phoenix harbors one of the largest black holes known. The presence of huge reservoirs of cold molecular gas in the central galaxy also informs mass estimates. Such gas provides a steady supply of fuel for accretion. If the black hole were only modest in size, this fuel would drive it to radiate at or above its maximum limit. Instead, the nucleus radiates strongly, but not excessively, implying a black hole massive enough to accommodate large inflows without breaching theoretical limits. The coexistence of rapid star formation, abundant cold gas, and vigorous but sub-Eddington nuclear activity points to a central mass capable of absorbing enormous inflows. Gravitational lensing offers an indirect global perspective. The Phoenix cluster produces arcs and distortions in background galaxies from which astronomers map the distribution of mass. While lensing measures the entire cluster, rather than the black hole itself, it confirms the extraordinary central concentration of mass. The brightest cluster galaxy dominates the core, and by association its black hole must scale accordingly. Though not a direct measurement, lensing supports the picture drawn from other methods. Together these approaches outline a mass range rather than a precise figure. Estimates for the Phoenix black hole typically fall between 20 and 100 billion solar masses. This range places it among the most massive known, alongside objects like TON 618 and other giant quasars. The upper end of the range would make it the largest supermassive black hole ever measured, though uncertainties prevent a definitive claim. What is clear is that the Phoenix black hole exceeds the mass of nearly all others studied to date, making it a unique case for understanding the growth of extreme cosmic engines. The uncertainty arises from both observational limits and theoretical extrapolations. Scaling relations are well tested for black holes up to a few billion solar masses, but less reliable at higher values. Cavity power estimates depend on assumptions about efficiency and duty cycles. Luminosity comparisons rely on corrections for obscuration and beaming. Each method carries systematic errors that expand the possible range. Still, the convergence of independent techniques on values tens of billions of solar masses gives confidence that the Phoenix black hole is indeed extreme. Why such a massive black hole exists in this cluster remains an open question. Theories of black hole growth suggest that early seeds formed from the collapse of the first stars or from direct collapse of gas clouds accrete matter for billions of years to reach giant sizes. In dense environments like cluster centers, mergers of galaxies and inflows of gas provide abundant fuel. The Phoenix Central Galaxy, with its long history of accreting satellites and its current starburst, fed by cooling gas, offers ideal conditions for sustained black hole growth. The resulting mass is the cumulative product of cosmic history, recorded in the present-day engine. The implications of such a massive black hole are far-reaching. Its gravitational sphere of influence extends across thousands of light-years, shaping the motions of stars and gas in the central galaxy. Its energy output, both radiative and mechanical, regulates cooling across hundreds of thousands of light-years. On even larger scales, it influences the fate of the entire cluster core, mediating the balance of heating and star formation. Phoenix shows how a compact object only light hours across can define the evolution of one of the largest bound structures in the universe. In considering mass estimates, Phoenix serves as a benchmark for the limits of black hole growth. Whether its black hole weighs 2050 or 100 billion solar masses, it demonstrates that nature has created engines at the very edge of known scales. The precise value remains uncertain, but the evidence leaves no doubt that the Phoenix cluster hosts one of the most massive, supermassive black holes yet observed. The possible mass range of the black hole in the Phoenix cluster extends into territory rarely encountered in astrophysics. Most well-studied supermassive black holes fall between a few million and a few billion solar masses, with the largest confirmed examples reaching tens of billions. In Phoenix, the estimates push even higher, raising the possibility of a black hole approaching 100 billion solar masses. Such a mass would place it at the very extreme of known cosmic engines, rivaling or surpassing all others measured. Determining whether this is the case requires careful consideration of uncertainties, yet even the lower limits mark Phoenix as extraordinary. The lower end of the range, around 20 billion solar masses, is already among the largest confidently inferred. This figure arises from scaling relations and the power required to inflate observed cavities. Even if these methods underestimate the true value, they indicate that the Phoenix black hole is not a typical central object but a giant. At the upper end, near 100 billion solar masses, the black hole would represent a category beyond current models of black hole demographics. Very few systems offer candidates in this regime, and Phoenix is one of them. The spread of values reflects both the difficulty of direct measurement at such distance and the limitations of applying relations calibrated on smaller systems. The importance of this range lies not only in absolute numbers, but also in what it reveals about black hole growth. Reaching tens of billions of solar masses requires sustained accretion over billions of years, efficient feeding mechanisms, and environments rich in fuel. The Phoenix cluster provides these conditions. Its central galaxy has merged with many satellites, adding both stars and gas. The intracluster medium supplies continuous inflows of cooling gas, evident in the observed filaments and reservoirs of cold molecular material. These ingredients create an ideal setting for prolonged black hole growth. If the upper mass estimates are correct, Phoenix shows how extreme environments can drive engines to the edge of possibility. Comparisons with other massive black holes highlight Phoenix's uniqueness. Quasars observed at high redshift, such as those hosting black holes of 10 billion solar masses when the universe was less than 1 billion years old, demonstrate that rapid growth is possible early in cosmic history. However, most nearby clusters show central black holes with masses only in the single-digit billion range. Systems like TON 618, with an estimated mass of about 60 billion solar masses, are rare. Phoenix falls within or beyond this category, making it a crucial data point for understanding the upper envelope of black hole growth. One of the key challenges in assessing the Phoenix mass is the reliability of scaling relations at extreme values. The relation between black hole mass and galaxy bulge mass, though robust at lower scales, may flatten or change slope for the most massive galaxies. Extrapolating it to galaxies as enormous as the Phoenix Central Galaxy introduces uncertainty. Still, the observed luminosity and feedback power support the idea that the black hole is consistent with such extrapolation. The agreement among independent methods suggests that while the exact number is uncertain, the object is firmly among the largest. The implications for galaxy and cluster evolution are significant. A black hole of tens of billions of solar masses exerts influence across vast scales. Its gravitational reach controls the motions of stars thousands of light-years from the core. Its feedback in the form of jets and cavities shapes gas across hundreds of thousands of light-years. Its growth history reflects the merging of galaxies and the cooling of the cluster atmosphere. Phoenix thus connects the smallest scales of relativity to the larger scales of cosmic structure. Understanding its black hole mass is not merely a matter of cataloguing extremes, but of tracing the links between processes across the universe. The mass range also informs limits on theoretical models. Simulations of galaxy and black hole growth predict that under normal conditions, supermassive black holes should plateau at a few tens of billions of solar masses as feedback halts further inflow. If Phoenix indeed harbours a black hole closer to 100 billion, it challenges these models, suggesting that under certain circumstances, feedback fails to fully regulate growth. The extraordinary cooling rate of the Phoenix core may provide such a circumstance, overwhelming the ability of feedback to halt accretion and allowing continued buildup of mass. Observations of the Phoenix nucleus in X-rays, optical and infrared all support the picture of a black hole radiating below its theoretical maximum. This sub-Eddington state indicates that the black hole is massive enough to accommodate large inflows without reaching saturation. If the mass were smaller, the observed luminosity would imply accretion at or above the limit which is not seen. Thus, the luminosity itself supports a very high mass. The exact figure remains debated, but the combination of cavity energetic star formation rates, cold gas supply and nuclear emission all point toward one of the heaviest black holes known. The question of whether Phoenix contains the most massive black hole in the observable universe cannot yet be answered definitively. The uncertainties in measurement, the rarity of systems with comparable data, and the limits of scaling relations leave room for multiple interpretations. What is certain is that Phoenix lies at or near the upper boundary. Whether it is the record holder or one among a handful of giants, its study informs the maximum scale of black hole growth allowed by nature. In this sense, Phoenix is not just another cluster, but a laboratory for testing the ultimate limits of astrophysics. Astronomers continue to refine estimates using new instruments. Improved millimeter observations of molecular gas may constrain inflow rates more tightly. High-resolution X-ray spectroscopy may clarify the energy budget of the core. Deeper optical spectra may improve measurements of emission line widths. Each advance narrows the uncertainty, but even without precision, the qualitative conclusion holds the Phoenix cluster harbours one of the largest black holes in existence. Its mass lies in a range that pushes the boundaries of understanding, marking it as an exceptional and indispensable system in the study of cosmic structure and evolution. The mass range inferred for the Phoenix central black hole allows astronomers to consider the scale of its defining boundary, the event horizon. The event horizon marks the distance from the singularity at which escape velocity equals the speed of light. Nothing, not even light itself, can cross outward once it has passed within this radius. For a black hole of millions of solar masses, the event horizon spans only a few million kilometers. For one of billions of solar masses, it extends billions of kilometers larger than the orbit of planets in the solar system. In the case of Phoenix, with estimates ranging from 20 to 100 billion solar masses, the event horizon would be staggeringly large. Even at the low end, the horizon would stretch farther than the orbit of Pluto from the Sun, encompassing a region of space measured in tens of billions of kilometers. This immense scale is difficult to visualize, yet it arises directly from the simple relation between mass and gravitational radius. The event horizon grows linearly with mass. Each additional billion solar masses adds millions of kilometers to the horizon's radius. In Phoenix, where the black hole may exceed most known examples, the radius of no return would outsize entire planetary systems. Despite this, the horizon remains minuscule compared with the galaxy and cluster it inhabits. The accretion disk extends only a few times beyond the horizon, and the disk itself is dwarfed by the central galaxy, which in turn is dwarfed by the cluster. This contrast illustrates how the smallest region in scale dictates energy flows that shape structures millions of light years across. The event horizon is not directly observable. Its presence is inferred from the behavior of matter and radiation near the core. Gas approaching the horizon is heated to extreme temperatures, emitting high-energy photons before crossing the boundary. Relativistic jets emerge from regions just outside the horizon, where magnetic fields tap into the rotational energy of the disk, and possibly the spin of the black hole itself. In Phoenix, the horizon cannot be imaged directly with current technology, but its effects are evident in the radiation jets and cavities produced. These phenomena trace back to a boundary that itself remains unseen, a one-way surface marking the edge of observable influence. The scale of the horizon also defines the sphere of influence of the black hole on nearby stars and gas. For the Phoenix black hole, this sphere extends thousands of light-years a distance over which the black hole's gravity outweighs that of the surrounding galaxy. Within this region, stellar orbits and gas motions are controlled by the central mass. In smaller galaxies, spheres of influence can be measured directly by tracking stellar velocities. At the distance of Phoenix, such direct measurements are impossible, but the principles still apply. The extraordinary horizon size implies an equally extraordinary gravitational reach. The gravitational time dilation near the horizon is profound. Clocks approaching the boundary tick increasingly slowly relative to those far away. From the perspective of a distant observer, matter falling toward the horizon appears to freeze and fade as light is redshifted to longer wavelengths. In reality, the matter continues inward, crossing the boundary in finite proper time. Though these relativistic effects cannot be observed directly in Phoenix due to distance, they are intrinsic to any black hole and define the environment near the horizon. The processes that generate radiation and jets take place in this strongly curved spacetime, where general relativity dictates the dynamics. The temperature and luminosity of the accretion flow also depend on the horizon scale. Larger black holes have cooler disks at a given fraction of the Eddington limit, because the gravitational potential per unit mass is spread over a larger region. For Phoenix, the disk may emit more strongly in ultraviolet and optical bands than in X-rays, consistent with the observed spectrum. The corona of hot electrons above the disk produces additional X-rays, but the primary radiation may be shifted toward longer wavelengths due to the enormous size of the system. This subtlety illustrates how the sheer scale of the horizon affects observable properties. The event horizon also defines the ultimate limit of information retrieval. No signals escape once matter crosses it. For Phoenix, this means that the billions of solar masses swallowed over cosmic history are forever hidden beyond the horizon, leaving only indirect evidence in the form of the black hole's present mass and its ongoing feedback. The horizon is thus both a boundary of space-time and of knowledge. In nearby galaxies, projects such as the Event Horizon Telescope have imaged the shadow of black holes like M87. In Phoenix, such imaging is far beyond reach, but the principles apply equally. If it could be resolved, the shadow would span microarc seconds on the sky, a scale too small for current instruments, but predictable from the inferred mass. The immense size of the Phoenix horizon emphasizes the link between black hole growth and cosmic history. Each solar mass added expanded the boundary by a few kilometers. Over billions of years, mergers and accretion enlarged the horizon from perhaps a few tens of kilometers at formation to billions of kilometers today. The horizon is therefore a fossil record of growth, a measure of how much matter has vanished into the singularity. While the process is irreversible, its consequences remain visible in the structures carved into the cluster and the radiation emitted by gas on its final approach. Comparisons with other massive black holes underscore the extremes of Phoenix. In the Milky Way, the central black hole has a mass of about 4 million solar masses and a horizon only 12 million kilometers across, less than the size of Mercury's orbit. In the giant elliptical galaxy, M87, the black hole reaches 6.5 billion solar masses with a horizon about 20 billion kilometers across. In Phoenix, even the minimum estimated mass pushes the horizon far beyond these values, and the maximum estimates dwarf them altogether. Such scales are rare and highlight the diversity of cosmic engines. Though the horizon itself cannot be crossed outward, its effects ripple outward across millions of light years. The jets that inflate cavities originate near it. The radiation that heats and ionizes gas emerges from matter approaching it, and the gravitational influence that controls stellar motions extends far beyond it. The event horizon is thus both a boundary and a source defining the ultimate region of no return, while powering observable phenomena across cosmic distances. In Phoenix, the horizon's size confirms the extraordinary nature of the black hole, marking it as one of the largest ever to shape a cluster's fate. Close to the event horizon of a supermassive black hole, the laws of physics manifest in their most extreme form. In the case of the Phoenix central black hole, the horizon is vast compared with those of ordinary galaxies, yet the principles remain the same. Gas and radiation approaching the horizon experience gravitational redshift, time dilation, and curvature of space-time that dominate all other forces. Although these effects cannot be directly resolved at the distance of Phoenix, their consequences are embedded in the signals we observe. The jets, the high-energy radiation, and the behavior of surrounding gas all trace back to the near-horizon environment where general relativity defines the rules. One key aspect of near-horizon physics is the slowing of time as experienced by matter approaching the boundary. To a distant observer, infailing gas appears to spiral more slowly as it nears the horizon, its emitted light redshifted to longer wavelengths until it fades from view. In reality, the gas continues inward, and crosses the horizon in finite time measured locally. This dual perspective is a fundamental prediction of Einstein's theory, confirmed indirectly in black hole studies across the universe. In Phoenix, where the black hole mass may be tens of billions of suns, the scale of this effect is magnified. The gravitational redshift of photons leaving the vicinity of the horizon is extreme, shaping the spectrum of emission from the accretion flow. The rotation or spin of the black hole further influences near-horizon physics. Spinning black holes drag space-time around them, an effect known as frame dragging. This twisting of space allows orbits closer to the horizon than in a non-rotating black hole, and may power the extraction of rotational energy to drive jets. In Phoenix, the presence of strong jets and cavities suggests that the black hole spin is significant, though its precise value cannot be measured directly. Models of jet launching rely on magnetic fields threading the horizon, tapping the spin to accelerate particles to relativistic speeds. Thus, even though the horizon is hidden, its rotational properties manifest across hundreds of thousands of light years. Another phenomenon near the horizon is the formation of the innermost stable circular orbit, the closest distance at which gas can orbit before plunging inward. For a non-rotating black hole, this orbit lies at 3 times the horizon radius, while for a maximally rotating one it can shrink closer. The position of this orbit affects the temperature and luminosity of the accretion disk. In Phoenix, the inferred emission spectrum is consistent with the disk, whose inner edge lies close to the horizon, suggesting that spin may bring gas deeper into the gravitational well before crossing the boundary. This in turn enhances the efficiency of energy release, increasing the power available for radiation and jets. Magnetic turbulence in the disk plays a crucial role in transporting angular momentum, enabling gas to spiral inward. As matter approaches the horizon, magnetic fields intensify and reconnect, releasing bursts of energy. These processes may explain the variability observed in many active nuclei. In Phoenix, the great distance smooths out short-term fluctuations, but integrated over time, variability contributes to the structure of cavities and jets. The magnetic activity close to the horizon is therefore imprinted on the largest scales of the cluster, linking microscopic plasma physics to macroscopic cosmic evolution. The extreme gravity near the horizon also bends light, creating the phenomenon of gravitational lensing on the smallest scales. If Phoenix's black hole could be imaged with sufficient resolution, the silhouette of the horizon would appear as a dark shadow against a background of glowing gas. This shadow, roughly 2.5 times the horizon radius in diameter, is the same effect imaged by the Event Horizon Telescope in M87T. In Phoenix, the shadow would be larger in physical size but far smaller in angular size, due to its distance making it inaccessible with current instruments. Still, the physics is the same. Photons orbiting close to the horizon trace a boundary that defines the observable shadow. The thermal radiation predicted by quantum theory, known as Hawking radiation, is negligible for black holes of such enormous mass. The temperature associated with Hawking radiation decreases with increasing mass, so for a black hole of tens of billions of solar masses, it is effectively zero on astrophysical timescales. The evaporation time far exceeds the age of the universe. Thus, the horizon in Phoenix is stable for all practical purposes, a permanent feature that grows only as more matter crosses it. This stability ensures that the black hole continues to serve as an anchor for the cluster core over billions of years. Within the near-horizon region, energy extraction occurs through multiple channels. Gas falling inward releases gravitational potential energy, part of which is radiated. Magnetic fields may tap the spin of the black hole itself, driving jets. Radiation pressure from the disk heats surrounding gas, while mechanical outflows inflate cavities. All of these processes originate within a few horizon radii, yet their influence extends across scales 1 billion times larger, reaching into the intracluster medium and regulating star formation in the central galaxy. Phoenix demonstrates how the physics near a horizon can dictate the fate of a system measured in millions of light years. The environment also includes transitions between different states of accretion. At high rates, disks are luminous and radiatively efficient, shining brightly across the spectrum. At lower rates, disks become radiatively inefficient, with energy carried away more by outflows than by light. Phoenix may alternate between these states depending on inflow conditions. The presence of both strong radiation and mechanical feedback suggest a hybrid mode where radiative and kinetic outputs are comparable. This complexity reflects the detailed physics near the horizon, where changes in accretion rate can transform the character of feedback. The immense mass of the Phoenix black hole also sets a lower frequency scale for oscillations and variability. The timescale for orbital motion at the horizon grows with mass so phenomena that occur over hours for stellar mass black holes unfold over years for supermassive ones. For Phoenix, variability tied to horizon scales could take decades or centuries. This means that observations capture only snapshots of longer processes, and the structures observed, such as cavities and jets, integrate activity over millions of years. The near-horizon physics drives phenomena too slow for direct human observation, yet their cumulative effects shape the cluster environment. Although the horizon itself remains hidden, the signatures of near-horizon physics pervade the Phoenix cluster. Radiation jets, cavities, filaments, and starbursts all trace back to processes occurring within a region only light hours across. In this way, the smallest domain accessible to general relativity influences the largest bound structures known. Phoenix exemplifies this connection, showing how near-horizon physics governed by relativity and magnetohydrodynamics sets the stage for cosmic-scale feedback. Its study bridges the gap between the most extreme predictions of theory and the grandest expressions of structure in the universe. The study of Phoenix reaches its limits when astronomers confront the boundaries of observation. At a distance of more than 5 billion light-years, the cluster is faint and compact in the sky. Even the largest ground-based telescopes with adaptive optics and the most advanced space observatories cannot resolve the innermost structures directly. The accretion disk, the event horizon, and the immediate region of jet launching remain well below detectable resolution. Instead, evidence comes from indirect signals, integrated spectra, X-ray brightness profiles, radio maps of extended lobes, and the distribution of cooling gas. These tools provide powerful constraints, but also impose uncertainties that define the edge of knowledge. The first limitation is angular resolution. To resolve the event horizon of a black hole requires microarc-second precision, achievable only for nearby examples such as the black hole in the Milky Way, or in M87. For Phoenix, the apparent size of the horizon is smaller by factors of thousands, far below current capabilities. This means the mass cannot be measured directly from the orbits of stars or gas close to the core. Instead, astronomers rely on scaling relations and energetic arguments, extrapolating from better studied systems. Such extrapolations are valuable, but increase uncertainty, especially at the extreme mass ranges suggested for Phoenix. A second limitation is sensitivity. Observing the faint outer regions of the intracluster medium at such distance requires long exposures with X-ray telescopes. Even then, noise and background radiation limit the precision of temperature and density measurements. These quantities are crucial for calculating the pressure balance and for estimating the energy of cavities. In Phoenix, the luminous core helps, but the outer structures are less certain. This uncertainty affects estimates of how much energy the black hole has released and how effectively feedback offsets cooling. A third limitation arises from timescale. The processes that govern feedback cycles operate over millions of years. Human observations span only decades. This means that data provides snapshots rather than continuous coverage. The state observed today may not represent the long-term average. Phoenix could be in a temporary phase where cooling dominates to be balanced by stronger outbursts in the future. Without longer baselines, distinguishing between transient states and permanent characteristics is difficult. Astronomers use statistical samples of many clusters to overcome this, but Phoenix remains an outlier whose rarity complicates comparison. Another boundary is wavelength coverage. While observations exist from radio to X-ray bands, each has its own limitations. Radio maps reveal jets and lobes but depend on the lifetime of relativistic electrons which fade over time. Optical and ultraviolet images show star formation, but are obscured by dust requiring infrared corrections. X-ray spectra reveal hot gas but are limited in resolution and sensitivity at high redshift. Millimeter observations trace cold gas but require extensive integration time. Each dataset contributes partial information, but no single wavelength captures the complete picture. Phoenix illustrates how multi-wavelength astronomy is necessary, but also how gaps remain. Modelling introduces further uncertainties. The conversion of cavity size into black hole power assumes certain efficiencies. The extrapolation of scaling relations assumes continuity beyond tested ranges. The correction of luminosities for obscuration depends on models of dust and gas distribution. Each step adds uncertainty. While the convergence of independent methods strengthens confidence, the true mass of the Phoenix black hole could lie anywhere within the broad range currently suggested. The inability to narrow this further reflects the limits of both instruments and theory. Despite these boundaries, Phoenix remains invaluable. Its extreme properties emphasize the importance of continued observation. Future facilities promise improvements. The James Webb Space Telescope has already begun probing the infrared spectrum of distant galaxies, offering new insights into star formation and dust. Next-generation X-ray observatories such as Athena will provide higher resolution spectra, tracing turbulence and cooling more precisely. Radio arrays like the Square Kilometre Array will map jets and lobes with unprecedented sensitivity. These instruments may reduce uncertainties, but even with them, direct imaging of the event horizon in Phoenix will remain beyond reach. The cluster's distance ensures that some aspects will always lie at the edge of observation. Theoretical work complements observation by exploring how such an extreme system could form. Simulations test whether feedback can ever fail to regulate cooling as it appears to in Phoenix, and whether such failure can persist long enough to create the observed starburst. They also examine how black holes can grow to tens of billions of solar masses without saturating at lower limits. Phoenix challenges models by presenting conditions that seem rare but must be possible. Its study helps refine theories of structure formation feedback and black hole growth. The limits of observation also highlight the importance of indirect inference. By studying cavities, astronomers measure past energy release. By analyzing star formation rates, they infer cooling inflows. By mapping cold gas, they estimate the reservoir feeding both stars and the black hole. Each measure is indirect, but together they form a coherent picture. The black hole at the heart of Phoenix cannot be seen, but its presence is unavoidable in the data. Its influence is written across scales from the smallest accretion structures to the largest intracluster atmosphere. These boundaries remind researchers that knowledge of the universe is always partial. Systems like Phoenix show both the power of current tools and their limitations. They invite new technology, new models, and new approaches. They also demonstrate the importance of extremes. By studying outliers, astronomers test the edges of theory. Phoenix is such an outlier where feedback is incomplete, star formation is extreme, and the black hole mass may set records. Even with uncertainty, its value lies in stretching the framework of understanding to accommodate possibilities once thought unlikely. Ultimately, the Phoenix cluster is both a window and a wall. It opens a view onto processes that connect the smallest and largest scales of the universe, but it also confronts us with the limits of what can be observed. The event horizon cannot be imaged, the exact mass cannot be measured directly, and the future evolution cannot be predicted with certainty. What remains is a system that reveals just enough to confirm its extraordinary nature, while concealing the rest behind the boundaries of resolution, sensitivity, and time. Phoenix stands at the edge of observational astrophysics, an object that defines the frontier of knowledge.